Kari? Hello everyone. So, good morning everyone. Good evening everyone. Good afternoon everyone. Are from the different time zone. So, welcome back to our fascinating journey through the natural language processing after captivating introduction to the NLP in our last session. Today premises even more insightful as we dwell into the intricate journey into the world of language modeling. So our district guy speaker need no introduction. Please join me in welcoming the Dr. Nikun Tail Ramani, a visionaries in the field, who will be our guide through the realism of the engram, RNN, LSTM, and the magic they wave in the tapestry of the languages. So Dr. Tail Ramani brings the wealth of the knowledge from his experiences, and today he will unravel the mysteries behind the language modeling and shedding the lights on the powerful tools in our arsenal, including the Ngram, RNN, LSTM, and GRE. So get ready to be the inspired and enlightened as we embark on this intellectual journey with the Dr. Tahir Ramani. So, build up as we explore the integrity of the language and witness the transformative impact of these models. So, without further ado, let's extend our warm virtual welcome to the Dr. Nikun Ramani. Over to you, Dr. Ramani, for what promises to be enchanting and enlightening sessions. Thank you so much. So, over to you, Nikun, sir.
So thank you very much, Ashish sir. So nice of you, and thanks for inviting me over here in this series of sessions. And it is wonderful initiative. So I must appreciate to all of you. Good afternoon, guys. This is Dr. Nikunj, and I'll be taking the session on the topics which are Ngram, RNN, so LSTM and GRE. So these are the today's presentation outline. Ngram approach. How Ngram is coming into the picture. So what you observed in the last sessions, where it was something about the bag of words, word to back, right? Now, in those particular cases, what is happening is that the sequence is very much important, right? When you convert those sentences into the vector form. So what was happening is each particular word was handled as the vector. Now, what is happening in that case is when you have the sentences like this. Here we have two sentences, R1 and R2. These are from the particular corpus. Now, the first sentence is about this pasta is very tasty and affordable. And the second sentence is the pasta is not tasty and it is affordable. Now, if you consider the bag of words representation for this, each individual word is treated as the vector. You remove the stop words. Those are the initial formalities that we do, lemmatization, stop words that we do in an initial part, and then we start applying the NLP approach. So, if you consider these two sentences, and after removing the stop words, again, very is also one of the stop words. So, if you remove the stop words from these two sentences, what is left with you? The things which are left is with you in sentence 1 is pasta, tasty and affordable. In sentence 2, pasta, tasty and affordable. Now, if you observe these two sentences, the sentences are exactly opposite in the sense where one sentence is saying that it is very tasty and another sentence is saying it is not tasty. But if you remove the stop words, what is happening is after removing the stop words, the sentences are same. So that is actually not acceptable. So what we need to do is we need to convey this sentence in a fruitful way by considering the meanings of those sentence, interpretation of those sentence in terms of very tasty and not tasty. Then and only then we can convey the fruitful meaning of these two sentences in that sense. So what is the approach? The approach is the first approach that we are already doing, that is a unigram approach, where we consider each word as a vector and we try to construct the vector based on the sentence given. In second approach, to avoid the previous limitations where the sentences interpretation semantics meanings are same due to this unigram approach, we can consider the bigram approach where we take two words at a time. So if we consider the bigram of the any particular sentence, let's say sentence R1, then it would be this pasta. That would be the first bifurcation. Then pasta is not tasty, and likewise. So where you have not tasty is considered as one of the vector. If you convert this sentence into the vector v1 or v2 as per their R1 and R2 review, then not tasty, very tasty, that will be coming under one of the vector. So here we are able to convey the meaning properly. And that's why bigram is one of the approach which is preferred over the unigram, because here we are able to get the sentence meaning or interpretation of the sentence. Same way, we have the approach of trigram. So in trigram, what we try to do is we try to club three words at a time. So that would be this pasta is very tasty, and so on. So that would be your trigram approach. So that will lead to the concept of n-gram. So the n equal to 1 is actually your unigram approach, which is the traditional approach that we are following. Then we go to the bigram, trigram, fourgram, and so on. So that will lead to the option of n-gram. So what we are able to retrieve from n-gram approach, which is always greater than 1. If I say n greater than 1, then it would be bigram, it could be trigram, it could be fourgram, and so on up to n-gram. So what is happening is we are able to retain the sequence information which is present in the sentence. That's what it is helping us to do so. So that is what is the n-gram approach, and that's why we used to prefer more than n greater than 1 particular approach. Either it could be bigram, trigram, and so on. But there is one limitation of n greater than 1. So when I say n greater than 1, it would be bigram, trigram, and so on. So when it is n greater than 1, the limitation is that as and when you increase the grams, it would be increasing your dimension. So when you convert your sentence into the vector, the dimensions are increased. So that is one of the limitation we can say if we go for more than n equal to 1 approach. So we need to make a trade-off that which particular approach we can follow. Obviously, we can start from n equal to 2 and we can figure it out that what is the best one which is good for us. Now, this is the probabilistic approach of this n-gram, where we start with the unigram. So in unigram, the probability of word, it does not depend on the past word. So generally, what we are doing over here is we are taking the context of the sentence. So context of the sentence means if I combine these two words, which is the present word and the past word, we can have the bigram approach. So that is a 2 in 1. Trigram, that is 3 in 1. So 1 present word and 2 past word. So this approach is actually useful for finding out or guessing the word. Even there are certain applications that we are going to discuss. So how it can be useful to us, or how you can talk this in English, or how you can say this in English, that probability of occurrence of word if you are having a last one word with you. Probability of occurrence of word in trigram approach given you have last two words with you. So that is having a very important applications. Like this is one of the application which is there. So let's say you have a sentence. Now the example is of guessing the word. So if I give you the sentence like this, and then slowly one by one I will reveal the words of the sentence at particular instance. Now what is happening is in instance particular one, first instance, your the one of the word revealed is my. Then second, click my. Then third is please click my. Fourth one is you please click my. Now, as and when we follow this kind of procedure to have a last sentence, obviously at particular stage you are going to guess that what can be inside this fill in the blanks. So if we have a normal traditional thinking, in that case, what is happening is if I see this click, then obviously click by the next word would be picture. So over here only I will be able to decide that what could be this the blank, where what can be inside this particular blank. So that would be picture. So that is actually important to understand, that how you can guess the word based on this bigram or trigram approach. So in this case, I'm having last two words with me, and I'm able to guess the present word. So that is again the trigram approach, where I can have these three as a trigram. Present word is the guessed word based on the past two, which is wn minus 1 and wn minus 2. So this is one of the application. Second application is automatic speech recognition. What is automatic speech recognition? How it can be helpful to us in this ASR approach? So let's say the sentence is the bear appeared from the shrubs behind the bushes. Now here the confusing word is the bear. Now it can be in a dilemma that is it bear, bar, means is it an adjective, noun, verb, and so on. So in that particular case, if I know the meaning of the sentence, then I would be able to call out that yes, this particular word, which is a confusing one, it can be a bear, which is an animal. It can be also helpful to us in checking the spelling in many software which are used for checking the spelling of the word which we write. So there are many times like we know that the verb following the adjectives, right? So in that case, we are able to retry that whether this particular sentence is a proper sentence, the word inside this sentence is which particular word, if the spell is wrong. So that's how it can be helpful to us by knowing the meaning or context of the sentence. So by following this, the language model that we are going to discuss first is RNN, recurrent neural network. Now, why we require recurrent neural network? So the applications are many. The first is maintaining a sequence of the words. So when we say that the multi-layer perceptron, which require vector as the input, so that is one-to-one. When we have a CNN, then we have an image as the input. But whenever we need to maintain the sequence of the words, so let's say the word is, let's say the sentence is the phone is very fast. The phone is very fast. Now, this fastness of this is related to phone, and very is related with reference to phone and fast. So in this, the sequencing is very much important. If you go to any other language, let's say I'm saying in English, I'm going out, and in Hindi it would be, if I go for the perfect translation, it would be मैं हूं जा रहा. So मैं हूं जा रहा is not the proper sentence. So sequencing is important in that case also. So where if you have this sentence, the sequencing is very much important, and sequencing is maintained in recurrent neural network. That is the first and foremost objective. We do have time series data, and time series data are always with relevance to the sequence. Whereas, like the New York has implemented the NYC concept in case of taxi demand and prediction. So, in particular timestamp, what is the demand of taxi cab in particular area? That is already listed in their websites, and by looking at those, the drivers can follow that and go into that area in that particular timestamp and have a ride quickly, and even customer get the service quickly. So time series data are always with relevance to sequence, timestamp 1, 2, 3, 4, 5, and so on. Machine translation. Machine translation means the English to Spanish or any other language translation. So if I don't give one whole sentence of English, I would not be able to get the first word of the Spanish or any other language in which you are interested to translate. So machine translation also require the whole complete sequence of English sentence, ASR, and image captioning. Image captioning is where you give one input, which is your image, and what is there inside that image, you are going to get in terms of sentence or text. So that is Google image search you have. Now, it would be more prominent if you have a text with you. So that would be Google text search. So if you give an image to the engine, it will be giving you the sentence. And that sentence, which is a text, then it would be a traditional Google text search where you will be able to retrieve the proper information. So there also we need a sequencing. So these are the primary areas where we need the language model like RNN, and which is the basic model. So again, why we need RNN? Why cannot we go for the simple traditional MLP multi-layer perceptron approach? Why can't we go for that directly? Why we need this RNN? So this is what is the example that let's say you have a 5-word sentence. The sentence is this phone is very fast. Now your vocabulary is having a 10k words, which are 10,000 words. Let's say your vocabulary is having 10k words. So each word is represented by 10k. So if you have a 5 words, then it would be total 50k that will be acting as your input. So here we are talking about the multi-layer perceptron approach. That why can't we model it with simple MLP? Why we are going for the RNN approach? So if you have a 5 words, each is represented with 10k dimension. So in total it would be 50k. You have a fully connected network. At last you have a classifier like softmax or log loss or whatever you have. Now what is happening is that in first case where we have 50k from the 5 words, let's say the next sentence is of 4 words, and that sentence is this phone is good. Now in this, the input will be of 40k. So length of the input is now changing. So if the input length is changing, ultimately it does affect the overall network. So the first problem is that length of the input, which is changing. So their MLP approach cannot be a good one for you. Second option is to remove this or to avoid this problem. You say that let's fix it to one particular value. So let's say that the fixed value is 50. So let's say the first sentence is of 10 words, second sentence which is x2 which is of 4 words, x3 of 15 words, xn of 20 words. So max to max, considering 50 words, you consider the input. So considering each word as 10k, your total size would be 500k, because we are considering a normalized factor or maximum factor which is 50. So now if I go for the first one, x1, where we have a 10 count, then that would be 100k. What about others? The remaining 400. So if I talk about x1, 10 into 10, 100. So it would be occupying your 100k. But what about the other 400k in the input? That is actually a zero pad. So we need to pad a zeros. Now, what it actually gives you, first problem is that you require a large network. Second point, let's say your query sentence is having 100 words. So here we are talking about training, but your testing stage, your query sentence is of 100 words. If you have 100 words, what will happen is that will be more than this 500k. If it is more than 500k, again, you will not be able to have a proper training and testing. So the output will not be proper because it is already exceeding the dimension of input, which is 100 into 100k. So in that again, we have a limitation of this proper MLP, traditional MLP approach. And again, if you have a large network, you need to train large number of weights, and those weights again that will increase the complexity. So that's why we don't consider MLP or multi-layer perceptron based approach while maintaining the sequencing of the sentence. So for that, what we use is RNN, recurrent neural network. Now, what is recurrent? Recurrent means repeating itself, unrolling itself for each sequence. So here, this is how the basic structure looks like, where these are your words of the sentence. So on x-axis, you have a time. At timestamp t1, we give the first word of the sentence. At timestamp t2, we give the second word of the sentence. At timestamp t3, we give the third word of the sentence, and so on. So what is happening is, this is what is your present input. Now, definitely we need some kind of weight over here. That could be 10H, sigmoid, and you have the activation unit, sigmoid, 10H, ReLU, whatever you have. You need the weight matrix. So let's say your input is d-dimensional vector. Your weight matrix, your weight is your activation function. Your activation function is having, let's say, 100 neurons. Let's say 100 10H neurons, or 100 ReLU neurons, or 100 sigmoid neurons. Then here it is d-dimension vector, which is your input. Here you have 100 neurons. So your weight matrix would be d cross 100. That will be connecting your input with the activation function. So you have to multiply this vector, that is a matrix multiplication, and you are going to generate the output. Now this output will be, again, goes to the next input. So that would be acting as the next input weight for one of the input of the next stage. The other input is always your present word, which is the second word of your sentence. So this is the present, this is the past. Now this is actually your 100 cross 100 vector. So this how it goes on. And at particular stage, you can retrieve the output. So here you can say that you have a sentence where we need to predict the sentiments, or sentiment classification problem, where we give the inputs of the sentence, or words as an input of the sentence. And the output is only one. So based on, let's say, 5 sentiments, so it is a 5-class classification problem. Or if it is a food reviews or that kind of thing, where we need to say that positive or negative, or we give the ratings 1, 2, 3, 4, 5. So based on binary classification, multi-class classification, we can have this one. So here also you can have one more classifier like softmax or log loss or so on. So this is how it repeats itself. So this is the basic structure or RNN, which gives you the idea that how you can maintain the sequencing of the words, where you give the input, first word at timestamp t1, t2, t3, t4, and so on, with the weight combination. So when you have the sequencing and the weights, obviously you will be having two concepts. One is forward propagation, and second is back propagation. So forward propagation is altogether in which direction your arrow is, which is in the forward direction. That's how you are going to have the forward propagation. That's very simple. But when we generate the output, now when we have the output and there is an error in output, so again we need to fine tune these weights. To fine tune these weights, we are going for the approach of back propagation. So in back propagation, what is happening is that, let's say you have these activation function. Now this is the same structure. Only the thing is that I have written this f, which is your activation function. I am giving the input, which is x, x1, x2, x3, xi1, xi2, xi3, which are the words of the sentence, right? There are some weights associated with the input. There are some weights which are being given as the last stage input to the next stage. And we have the output like O1, O2, O3, and so on. And at last, you have some kind of mechanism to check your loss function, which is loss function can be a log loss or any other loss function. So if you are writing the back propagation for this, or if you go for the back propagation funda, then how you are going to have this back propagation? If you write down the equation, then we need to follow the opposite direction of the arrow, because we are going from last to first. Means what we are checking is that what is the impact of first on the last one, which is your final output. That's what is the objective of back propagation. So what is the impact of first? So we need to start from last and we need to go step by step. At each stage, we need to apply the chain rule. And by following the chain rule in the opposite direction of arrows, we can reach up to the first one. So that would be giving us the loss function in the form of partial derivatives. That is what is your calculus. So if you look at this formula, then in that, if I want to write the loss function with respect to this O10, loss function with respect to O10, then it would be dou L by dou yi cap, which is your predicted yi. Yi cap means the predicted yi, which is different than the actual yi or same as the actual yi, into your yi cap divided by O10. This is the first chain rule we can apply. So what we are going to have in this chain rule, if I apply the back propagation, we are going to involve the weights. Which weights? Input weight, the previous weights, and the last weight, which is given as the final uh, classifier, which is softmax. So there are three weights over here. One is W, which is given as the input, W dash, which is coming from the previous stage, and W double dash, which is given as the final weight input to the final classifier, which is your softmax or log loss. So we are trying to adjust these weights by writing this back prop and adjusting those weights. So in your equation, you are going to have W dash and W double dash. So what is happening is, if you go for this kind of thing, what will happen is that if these partial derivatives are less than 1, what will happen is you are having a chain rule. Now, chain rule means it will start from last and it will go up to first. So it will be involving many partial derivatives into it. So del of yi up to del of w. That is the last xi1 part. So what will happen is that your multiplication of partial derivative will result in less than 1, because your partial derivative value itself are less than 1. So that will lead to the problem of vanishing gradient. At the same part, if your partial derivative values are greater than 1, if you multiply several partial derivatives starting from the yi cap to the xi, what will happen is the value will exceed the maximum value, maybe then 100. That will give the problem of exploding gradient. So that's why this back propagation approach in the case of RNN will give you the limitation of RNN. So that is the limitation of RNN. Now, how many types of RNN which we have? So first is one-to-one, that is simple multi-layer perceptron approach. Second is one-to-many, where you can have an example of image as an input, and you are going to generate the sentence from that given image. So you give the image to the CNN network, and after that you will be having a word sentence. That sentence will be given as a part of embedding to word to back or glove, and you are going to have the vector translation of that sentence. So that is the one to many. Third is many to one. So where again you have sentiment analysis, you give number of words and you're trying to predict the sentiment. Then there are two variants of many to many. First variant is the approach of language translation or machine translation. Machine translation, where you have English as the input and you are going to generate the next language after the translation. So until and unless you give the last word of the English, you are not going to have the first word of, let's say, the Spanish. So we are going for English to Spanish translation. So that is the first approach in many to many, first variant of many to many. Second approach is your simple part of speech tagging approach, where we give words of the sentence as an input and we are trying to predict whether it is a verb, whether is it the objective adjective, is it a noun or so on, whatever the different part of speech are. So this is the many to many, but you have the instant output, which is the example of part of speech. Now, what is the problem with the RNN? First is the derivatives. Second is the problem of long-term dependency. Now, if we see this diagram, what is happening is that, let's say, this stage ht plus 1, which is your output. This output is mainly depending on present input and the past input. But in sequencing, what is important is you should be having an impact of the first word onto the next fifth output also. So that's how we maintain the sequence. And that's what is this example was, where until and unless we have the whole English sentence as an input, we cannot get the first Spanish word. So what is the problem over here in RNN is that this HT plus 1 is mainly depending on XT plus 1 and the previous HT minus 1. It should not happen like this. This HT plus 1 is having a bigger impact of X0 also. It's having bigger impact of X1 also. But since there are very far away, there are many layers in between. There are very dense layers are there in between. The impact of X0 may not be there on HT plus 1, or there will be very little impact on HT plus 1 due to change in X0 or X1 due to large network. So for that, what we have is we can have the another language model, which is your LSTM. So what is LSTM? What we do in this? In this, we are trying to cascade the two inputs. So here we were trying to sum the two inputs in RNN approach. Now in LSTM, we are trying to cascade the two input. Now, what do you mean by cascading? Cascading means there are some weights over here on the past input. There are some weights over here on the present input. That will be cascaded and the two respective activation function. So that would be your, here there is a 10H activation function. Your past input is having some value. Your present input is having some value. That values are cascaded and your weight matrix are cascaded and that are given as the input to your 10H function. So you can generate the HT, which is your output, and the same is given to the next. So the problems are long-term dependency and the multiplication with the smaller weights. That is the derivative. That is being solved using this LSTM. Now, how it will solve this? Let's see the simplified structure of LSTM. Now, there are three different gates over here. And this LSTM is dealing with the cell-based approach. So if I say this square box is one cell, this square box is one cell, this square box is one cell, and so on. So what is happening is that how to avoid this long-term dependency or how to carry this input directly to the next state without considering the intermediate state. We have something called as forget gate. So how forget gate will behave is that it will try to remember what is important to remember, which you can carry to the next state, or else you can directly make it zero so that your past will directly go to the next. There is one more input, which is input gate, and the third is your output gate. So let's understand this with this diagram. So in this diagram, what is happening is that this is your previous cell state output. This is your forget gate, where it is having some activation function, and that activation function is sigmoid activation function. Sigmoid is always having a value between 0 to 1. Why it is kept 0 to why it is kept over here in forget gate? Because if this value is 0, then you will not be having anything as a part of input from the forget gate. So whatever is your previous will not be carry forwarded to the next state. Instead, you are going to get something from the input gate only. You are not going to get anything from the past. And that's why this is the multiplication sign. Now, if this input is 1, which is if the activation function, which is your sigmoid activation function, is 1, whatever was your previous cell output can be directly passed to the next state. At the same time, you're going to have the input also. And that input is your present input. So if you look at each and every gate, you have two different inputs. One is your present input and one is your past input, which is xt and ht minus 1. Ht minus 1, which is your previous input, which is over here like this. Ht minus 2, ht minus 1, and so on. So these are the previous outputs. This is the present input that are given as the two inputs to each and every state. So if it is 1, directly it can be passed. At the same time, you have an input gate. In input gate also, you have the activation function, which is your sigmoid activation function. Now, if this activation function is 1, then this will be directly passed to this summation block. If this is 0, the input will not be passed. So that is again the criteria for input gates. Same way, you have an output gate where you have a sigmoid activation function. If it is 1, it will allow the output to propagate to the next layer. If it is 0, it will be not allowing that. So, and these are the peepholes. So peepholes are that you can also give your cell state as the one of the input apart from your recurrent input and the present input. So past input and the present input. This input is nothing but your past output will be acting as the past input. Input is your present input and your forget gate. So your ht minus 1, xt, and your peepholes, which are your cell states, which you can directly give it to this summation block. So the main beauty of this LSTM structure is you can also give states, which are the output state, which can adjust your input. So every gate is having the allowance of 0 and 1. That's why there is a activation function which is your sigmoid, either 0 or 1 or anything in between. Let's say I want to carry 50% of the past. So if I want to carry 50% of the past, my sigmoid will be having a value 1 by 2. So anything will be passed from this will be multiplied with 1 by 2, that is multiplied with the 50%. So you are going to get the half of the previous result. So it depends what you have as a part of activation function. So here we are avoiding limitation number 1, that is multiplication with the weights, which are the smaller, to avoid that backprop problem of vanishing gradient or exploding gradient, because now we have this structure where we have a weight which are generated from the input and the recurrent part. And the second is you can directly carry your past input, a past cell output to the present or next cell, which is direct propagation, like a ResNet. Like a ResNet. In ResNet, we can directly avoid and create an identity mapping from input to the output by avoiding the in between cells or layers. So this is how the LSTM can help you in that case. So these are all activation function which are segvoid, and here you have the activation function which can be tan h. So tan h, why? Because we don't know, like tan h is -1 to 1. The value of tan h is -1 to 1. So when we pass this previous cell output, if that is itself 0, we'll get the output 0 of this, or maybe this activation is 0. So we are not able to carry forward that. So we are not able to find out that whether the previous cell output was 0 or activation function was itself 0. So that's why we need a tan h over here. And at every other stage, we have a sigmoid activation unit. So this is the cascading diagram. So let's understand this same procedure quickly, one by one. So this is your previous cell output. Now, if you want to carry this output directly to the next cell or present cell output, you provide all zeros to this. So here you have a sigmoid activation function. So this is what is your input gate, where you have two input, xt, which is your present input, and past input, which is a recurrent input, ht minus 1. So if this is 0, so you're not going to get uh, anything from here. But if it is 1, you can directly pass this. So if this summation is 0 and this multiplication is 1, you will be able to propagate this ct minus 1 to ct. Given a condition, all input to this second input to this multiplier is 1, all input to this summation is 0. You will be able to take ct minus 1 is equal to ct. You can also put 1 by 2 over here, 1 by 2, 1 by 2, 1 by 2. That will be pointwise multiplication with the ct minus 1. The weight multiplication with ct minus 1, which is a pointwise multiplication. So that will be carrying your 50% from the previous. And here you have an input gate. This is what is your input gate. And this is what is your output gate. So the same structure is drawn over here like this. So if I consider the first case, here it is sigmoid of cascading of weight, which is weight at this input, which is ht minus 1, weight at this input, which is xt. So that is combined weight, which is w of f, into ht minus 1 into xt, plus bias. You can consider bias, or you can also ignore the bias. Then second stage is your input gate, where you have I of t as one of the input to the multiplier, and the second input is ct. So the first input is allowing your input to propagate, and second input is from the tan h activation function. And third one is your output gate, where you have the output is given as the input to the next, or it is also can be copied to somewhere else. So this is called as a copy operation. The output is copied and propagated to next state, or it can also be retrieved and give it to one of the yi, which is the softmax or log loss. Now, if I consider this particular criteria, in this particular criteria, if this is 1, this particular input is always 0. So either of them will be negative, either input or forget. So what we can say that input is equal to 1 minus forget, or forget is equal to 1 minus input, because either of them will be in the activation. So that is called as gated recurrent unit. So instead of increasing the complexity by treating these weights or training these weights or adjusting these weights individually, if I am having forget gate output is equal to 1, which is the activation function is 1, your input gate is 0. At the same time, if your input is 1, your forget is 0. So that is called as gated recurrent unit, which is your simplified structure of LST. So that's why it is 1 minus criteria, which is given over here. So this is your faster version of the LSTM, more faster, less complex because we don't have that many number of equations. We don't have to train that many number of weights. And again, both of these are popular. So this is your gated recurrent unit. So this was about the introduction of LSTM, RNN. What is the limitations of RNN? How we can solve that using LSTM? What are the limitation of LSTM? And what are the different things are there in the GRE? So that's where I would like to conclude my session. So if you have any question, you can think over it.